Hello, my name is Ronaldo de Lima Cardoso. I will present the paper entitled Experimental Study at Hypersonic Shock Tunnel of a 3D prototyped scramjet powered with hydrogen. In this presentation, I will talk about an introduction, scramjet technology, hypersonic shock tunnel, results, conclusion, and acknowledgements. Efforts in research and development of scramjet technology by several research centers around the world is due to the potential to increase the payload and reduce the cost of satellite launch vehicles. The research of scramjet engines has been developed for over 40 years. In Japan, the studies were carried out at Scramjet Engine Test Facility in the Japan Aerospace Exploration Agency. A lot of effort were done to simulate flight conditions with a Mach number varying between 84 to 80 to understand the supersonic combustion mechanics. In South Korea, since 2005, studies of the scramjet technology were done in Korea Aerospace Research Institute. The first objective was to collect data of the fundamentals physics and characteristics involved in scramjet engine simulating flights with Mach number 7.6. The USA is the most successful country to demonstrate the scramjet technology in flight, with the flight experiments of X-43 and X-51. The scramjet engine is a hypersonic air-breath propulsion system. When an object is in a supersonic or hypersonic flight, a phenomenon called shock wave is established. The temperature, pressure, and density of the airflow are increased through the shock wave, while Mach number and velocity decreased. The admission is where the airflow captured by the scramjet inlet is compressed, heated, and decelerated by shock waves generated during the hypersonic flight. The airflow enters the combustion chamber at supersonic speed. In the isolator, the shock waves are attenuated and the fuel is injected and mixed with the airflow in supersonic speed. The combustor section is where the supersonic combustion starts. In the nozzle, the products generated by the supersonic combustion are accelerated to hypersonic speed, generating the enough thrust to the hypersonic flight to be realized. A hypersonic shock tunnel is the best tool to experimentally simulate the flight conditions of the hypersonic flow over a scramjet engine geometry. The shock tunnel is formed by two reservoirs with different pressure, one with higher pressure called driver and other with lower pressure called driven. These two reservoirs are separated by one or more diaphragms. In the end of the driven section is installed another diaphragm to separate these regions of the test section. Also, in the end of the driven is coupled a convergent-divergent nozzle. The test starts with the rupture of the diaphragm that separates the driver and driven sections. In this moment, the gas inside the driver expands to the driven, creating an incident shock wave which propagates through the driven. These shock waves encounters the diaphragm installed at the end of the driven and breaks it. The quasi-stagnated airflow is then accelerated to the desired speed by the convergent-divergent nozzle. The experiment of this work was realized in the T3 hypersonic shock tunnel of the Professor Nagamatsu laboratory at the Instituto de Estudos Avançados. The academic Scramjet model used in this work was prototyped by a 3D printer. This model has 1.2 meters long and a total of 32 pressure transducers, but it's important to say that the region analyzed in this work is the combustion chamber, where the pressure transducers identified as P13 to P24 were installed. The experiment carried out in this work has three different setups: experiments with injection of hydrogen, experiments with injection of helium, and experiments without injection, to be used as a baseline in comparison between the experiments. 13 experiments were done. Experiments without injection 1, 2, and 3. Experiment with 15 atm hydrogen injection, experiment 4. Experiments with 14 atm hydrogen injection, experiments 5, 7, and 8. Experiment with 80 atm hydrogen injection, experiment 6. Experiment with 5 atm hydrogen injection, experiments 9 and 10. And experiments with 14 atm helium injection, experiments 11, 12, and 13. Here is present a normalized measurement obtained by a pressure transducer, the line in blue, with its median in red. To facilitate the visualization of the measurements, the graphics will present the median values of each pressure transducer. This normalized pressure is calculated by the ratio of the pressure measured with the flow pressure obtained in the leading edge of the model, which is obtained by a method and calculated by an in-house software. First, it's important to say that the injection occurs at 820 millimeters from the leading edge, in the bottom wall of the combustion chamber. The pressure mentioned in the description of the experiment is the value in the fuel system, with the fuel pressure in the experiment being almost half of this value. The pressure transducers P13 to P15 are installed before the injection. Here in this figure we have the upper wall measurements comparison between experiments 1 and 2 without injection and experiments 12 and 13 with helium injection. It's possible to see that after the position of the injection, the greater measurement variation between the experiments were presented in P18 and P19. Here in this figure we have measurements obtained in the bottom wall of the combustion chamber. The pressure transducers P23 and P24 not obtained measurements in almost all experiments. In this figure, we have the measurements obtained in the upper wall of the combustion chamber for experiments with injection of helium, experiment 12, injection of hydrogen, experiment 6, and experiments without injection, experiments 1 and 2. It's possible to see that the results obtained in the experiment 6 presented higher measure in P20 and P21. However, also it's possible to see that this difference is small. In this figure, we have the measurements obtained in the bottom wall of the combustion chamber for experiments 1, 2, 6, and 12. Again, it's possible to see that the results obtained in the experiment 6 only present a difference in P19 measurement, with this difference being again small. In experiment 6, the pressure transducer P24 obtained a measurement. This figure shows the comparison of measurements from the upper wall between experiments 4 and 5, experiments with hydrogen injection, experiment 11 with helium injection, and experiment 1 without injection. Only pressure transducer P21 showed higher value in experiment with injection of hydrogen. Here is presented the comparison of measurements from the bottom wall between experiments with the experiments 4, 5, 11, and 1. In this figure, the pressure transducer P22 and P24 obtained higher values in experiment with injection of hydrogen. This figure shows the comparison of measurements from the upper wall between experiments with hydrogen injection 7, 8, 9, and 10, and experiments without injection 1, 2, and 3. In this figure, only the pressure transducer P18 showed the higher value in experiments with injection of hydrogen. All other obtained measurements lower than in experiments without injection. Here is presented the measurements from the bottom wall between experiments 7, 8, 9, and 10 with hydrogen injection and experiments without injection 1, 2, and 3. In this figure, only the pressure transducer P19 showed higher value in experiments with injection of hydrogen. This paper shows the experimental study of a 3D prototyped academic Scramjet model tested in the T3 Hypersonic shock tunnel at the Instituto de Estudos Avançados. It was expected to obtain the rise in pressure by the measurements after injection point, with this rising spreading through the combustion chamber. In the measurements obtained in the upper wall, the rise in pressure are only detected by the pressure transducers P18 and P21, but not in all experiments with hydrogen injection. In the measurements obtained in the bottom wall, the rise in pressure are only detected by the pressure transducers P19 and P22. The pressure transducer P24 only worked in experiments 4, 5, 6, experiments with injection of hydrogen, and experiment 11 with injection of helium, with the first three obtaining a higher value when compared with the last one. The results obtained by the pressure transducers in the experiments carried out showed that the expected rise in pressure caused by the supersonic combustion was not detected. It is important to say that another work using a diagnostic technique has been done and detected the supersonic combustion. However, only the pressure transducers not allow this identification. Finally, it's possible to conclude that the supersonic combustion in this 3D prototyped academic model was not conclusive by the analyzer results. I would like to thank the Instituto de Estudos Avançados for the support given to complete the scientific work, allowing the use of the necessary equipment to develop and analyze the data of the experiments. I also Would like to thank the próprio Hyper Project and Coordenação de Aperfeiçoamento de Pessoal de Nível Superior, CAPS, for the financial support. Thank you.